Okay, welcome everybody to the top of page 104 in the workbook. Okay, and on this page, we're going to introduce a little bit more terminology and talk about a few theorems that are going to lead us to another criterion for determining if a linear operator is diagonalizable. Okay, so we'll start with the definition. Okay, this relates to eigenvalues of a linear operator, and it's called the multiplicity of an eigenvalue. And basically, what multiplicity means is it's the number of times that eigenvalue appears in your characteristic polynomial. You kind of remember the process for doing this, finding eigenvalues. So you take the determinant of a minus lambda I, you do some algebra, you get a big polynomial, and it's going to factor, and some of those factors have powers bigger than 1. Okay, and so that k, the number of times that factor is repeated, that's the multiplicity of your eigenvalue. Okay, that's going to give us another criterion in a minute for determining diagonalizability. Okay, there are a couple of theorems though that come first. Okay, so if we look at the box right below this, okay, let's suppose that we have a linear operator again, and a list of k distinct eigenvalues, lambda 1 through lambda k. Okay, we can form a characteristic polynomial. Okay, and you can see that in this form, the R1, R2 up to Rk, those are the multiplicities of the eigenvalue, according to the definition above. Okay, and the first thing we can say, Theorem 5.5, tells us something about the eigenvectors. Okay, so we're going to assume that each vi is an eigenvector associated with lambda I. Turns out, if you put all of those eigenvectors into one bag, S, they have to be linearly independent. What is that really saying? Well, it's just saying that if you have a bunch of eigenvectors and they all come from different, that's this distinct eigenvalue, they have to be linearly independent. Okay, we don't have to check that if we know that each eigenvector comes from a different eigenvalue. Okay, and there's one other thing that we can say. That's Theorem 5.7 here. Okay, it tells us something about the size of the eigenspace. The dimension of E lambda I is always between 1 and Ri. What is that saying? Well, let's take it one inequality at a time here. Okay, so the fact that 1 is less than or equal to the dimension, that's just saying that every eigenspace has to have at least one linearly independent eigenvector. It's not possible that we have no eigenvectors with an eigenvalue. Okay, and then what about the other inequality? Well, remember what this number Ri represented again. It was about the multiplicity of our eigenvalue. Okay, so it's basically saying that we can never get more eigenvectors than we have for the multiplicity of whatever our eigenvalue is. So the multiplicity is an upper bound, if you like, on the number of linearly independent eigenvectors that we can get. Okay, and so now that we have this terminology behind us, we can state Theorem 5.9, which is a big result about diagonalizability. It gives us another way to think about it. Okay, so we'll start kind of with the same assumption that we did above. Okay, assuming that we've got a list of distinct eigenvalues, lambda 1 through lambda k. Okay, and part A of the theorem says that T is going to be diagonalizable if and only if the multiplicity of the eigenvalue is always equal to the dimension of the eigenspace. So if you can get those two numbers to match each other, okay, for every multiplicity of an eigenvalue in your characteristic polynomial, if you can find that many eigenvectors, then you know that your linear operator is diagonalizable. Okay, and what kind of comes out of that is a way of arriving systematically at a basis of eigenvectors for your entire vector space. Okay, what you can do is kind of attack this one eigenvalue at a time. Okay, and for each lambda I, you can find a basis beta I for that eigenspace. And provided that you start with a diagonalizable operator, you can throw all of those bases together into one bag, and you get a basis beta, okay, for your entire vector space. And that basis contains only eigenvectors. Okay, so in future examples, we will put that theorem to work for us.